So let's warm up a little bit here with a couple of problems as we introduce this concept of implicit differentiation. Okay? So this first one here, we have y equals 4 times the sine squared of 5x. And we want to find y prime. What are we going to have to use to find the derivative here? The chain rule, okay? Chain rule. We have a sine function, we have the 5x function, we have the squared function. There's 3 different functions going on here, right? And we got to figure out which one is outermost. So what's the outer function on this one?
Squared.
Yeah, it's the squared, okay? So you can view this as 4u squared, where u is the sine of 2x. Okay? Now, y prime...
I just 2x and 5x.
Oh yeah, 5x, sorry. Thank you. Okay? So y prime is going to be the derivative with respect to u. In other words, the derivative leaving u alone inside of it. And then times the derivative of u itself. Okay? So let's find the derivative of u. What's this du dx here? Cosine of 5x times 5, okay? So there we have the chain rule again. Okay? We've got the chain rule again. And so the derivative of sine is cosine. Then the derivative of 5x is 5, so we're multiplying that by 5. Okay? So now we're ready to do y prime. Okay? What's the derivative of 4u squared?
8u.
8u. So 8u times du dx, and we plug u back in. So we have an 8 times sine of 5x times 5 times the cosine of 5x. And then we can put that together. We've got 40 sine of 5x cosine of 5x. Okay? Does that make sense? Okay. All right. 40 sine of 5x cosine of 5x. Now this one poses us with a little problem here, okay? We want f prime of x. Well, right now, we have xy equals 6.
Could you divide both by x?
All right, we're going to divide both sides by x. That'll make it y equals 6 over x, which I could express as f of x. All right? Now that it's in terms of just an x, y is in terms of x, we can write that as f of x. Okay? And of course, I can rewrite 6 over x as what?
6 times x to the negative first power.
Yeah, 6x to the negative 1. Okay? So, what's f prime?
Negative 6x, negative 6 over x squared.
There you go. Negative 6x to the negative 2's, which is negative 6 over x squared. Okay? And then I could easily then plug in 2. Okay? Again, this is notation that you should be familiar with. If it's f prime of 2, you're just plugging 2 into the derivative. Negative 6 over 2 squared.
Negative 3 halves.
Negative 3 halves, yep. Negative 6 over 4, which is negative 3 halves. Okay? Okay. Now, the reason why I used this function here as kind of an introduction today, a little bit of a warm-up, is because we have an example here of what's called an implicit function. Okay? An implicit function as opposed to an explicit function. Okay? Now, an explicit function is when the variable y is explicitly written as a function of x. In other words, it's y equals something x, okay? And something with x's in it. All right? So, what we did, well, with our first one on A up there, y equals 4 sine squared of 5x. That's an explicit function, okay? Initially, b was not an explicit function. We had to rewrite it like this to make it an explicit function, okay? So this first one was an explicit function. The second one we were able to write as an explicit function. Okay? Now, an implicit function cannot easily be written to express y as a function of x. Okay? It cannot easily be written to express y as a function of x explicitly. So here you see the example we did above, xy equals 1 is the implicit form. Explicit form is y equals 1 over x, and then we can take the derivative really easily. Okay? Now, here we're taking the derivative explicitly. However, I want to take a look at an example like this where we could figure out the answer explicitly, but look at what's known as implicit differentiation. Okay? And that's what we're going to do here with xy equals 6. Okay? So just like the one that we had above, xy equals 1, we're going to rewrite, or we could rewrite this as y equals 6x to the negative 1. And that would mean that dy dx, or f prime of x, okay, would equal a negative 6 over x squared, just like we had above. Okay? Now, I'm telling you, that's what we will get the answer to be in the end. But that is all done explicitly. Let's do this implicitly. Okay? So, when I'm doing this implicitly, I'm going to view this as x times y equals 6. Okay? Now, what I'm going to do is I'm going to take the derivative with respect to x on both sides. Okay? So, the derivative with respect to x of the product x times y is going to equal the derivative with respect to x of the constant 6. Okay? Now, let's look at this carefully here. What's the derivative of a constant?
0.
0. Okay. What am I going to have to use to find the derivative on the left-hand side here?
Product rule.
The product rule. Okay, the product rule. Now, let's watch this. First of all, I need to take the derivative of the first factor, which is derivative of x, which is 1, times the derivative of the second factor. Right?
No, not the derivative of the second factor.
Times the second factor, sorry. So I have 1 times y. I need to add to that the first factor times the derivative of the second factor. What is the derivative of the second factor?
Negative 6 over x squared.
No. It's just, because we don't know that, okay?
Y prime.
It's y prime. Or, this is notation we'll use a lot, dy dx. Okay, in this unit we'll actually use this notation a whole lot, so, or in this part of the unit. Okay? So, remember our whole purpose is to find f prime of x. F prime of x is the same thing as dy dx, right? So now I can use algebra to solve for dy dx. So dy dx is going to equal a negative y
Minus x.
divided by x. I subtract y from both sides, then I divide by x. So we have negative y over x.
We're just drawing a surface.
Well, what is y? Y equals 6 over x, right? So if I wanted to, I could make this a negative 6 over x, which would be a negative 6 over x squared, just to make it match up with
Whoa.
what it was up here.
Wait, where'd you get? Oh, right, here.
Okay? Now, you're not going to be able to do this last part on all of these. In fact, if you could, then you should have done it explicitly in the beginning.
Yeah.
Okay? But you're going to end up with an expression that has both y's and x's in them. So to find the derivative at a point, you're going to have to plug in the x coordinate and the y coordinate of the point. Does that make sense? All right? So again, this is one where we could have done it explicitly, but that would be doing it implicitly. Okay? Now, let's look at a couple of other examples, just simple examples to try to get the hang of this, all right? If I am finding the derivative of y cubed with respect to x, okay? Notice what we're really using here is the chain rule. Okay? We know that y is some function of x, we just aren't able to express it here. So notice what we're doing. To find the derivative with respect to x, we have to take the derivative of y cubed with respect to y times the derivative of y with respect to x. You see the chain rule in there? Are you seeing it? It's kind of like the dy du times du dx, and the du's cancel. All right. The difference here is we don't know what u equals, so you can't plug it back in. You're going to have that, in this case, y in your answer. All right. So if I were differentiating this, what's the derivative of y cubed with respect to y? Yeah, it's just 3y squared. But, chain rule, you got to multiply by dy dx. So that is the derivative of y cubed with respect to x. And that is your answer. Okay? So it's 3y squared dy dx. Okay?
So, in this case, are we looking, like, what do you do with the d over dx, y cubed?
Here, you're taking the derivative of y cubed with respect to y. So that's just like a normal power rule derivative. The derivative of y cubed is 3y squared. The problem is that we weren't asked to find the derivative with respect to y, we were asked to find the derivative with respect to x. So now we've got to use the chain rule and multiply it by the derivative of y with respect to x. That's what this dy dx on the end is.
Oh, so like, in terms of notation, when it says differentiate with respect to x, on the left side of the equation, that's like the notation.
The original
that we're
problem.
looking for, x,
Yeah.
the differentiate with respect to x.
Mm-hmm.
Oh,
Yeah. Yeah, and again, notice here, this is all the chain rule because y is some function of x. Okay? If you remember, when we did y equals 2u and u equaled whatever, or I'm sorry, not 2u because that's too simple, u squared, then when we did dy dx, we did 2u times whatever du dx was. It's the same thing here, guys. The difference is that we don't know what u actually equals. We don't know what y actually equals in respect to x, so we just have to leave dy dx there. Okay? So that's what we're trying to do here, is find this derivative with respect to a different variable. Okay? Here's another one, dy dx equals x, or of, sorry, let's start over. The derivative with respect to x of x plus 3y. Okay? Now, what's the derivative of x? 1. Okay? The derivative with respect to x of 3y okay, is going to be the derivative with respect to y times the derivative of y with respect to x. What's the derivative of this with respect to y? 3 times the derivative of y with respect to x. Okay? So our answer in the end is just 1 plus 3 dy dx. And that is the answer. That's all you can do with that. Okay?
I'm kind of confused.
Okay.
It is a little bit confusing. Basically, here's the rule. Okay? If you can get this down, this becomes so much easier. If you're taking the derivative with respect to one variable of something that is in terms of a different variable, just take the derivative like normal and throw a dy dx or dr dx or whatever on the end. Multiply by it. cause it's the chain rule every time, okay?
If you're doing, if you are differentiating something with respect to x,
Mm-hmm,
that means it's gonna be d something over dx.
yeah,
Gotcha.
you're gonna have that. So, here we have, what are we gonna use to find the derivative of x times y squared? Product rule, okay? So, we have the derivative of x, which is 1, times the original second factor, plus x times, and then here's where the implicit differentiation,
2y dx.
we've got the derivative with respect to x of y squared. Okay? So, I know it's y squared plus x times something. What's the derivative of y squared if I were doing it in terms of y?
2y.
It would be, it would be 2y, but since we want it in respect to x, you tack on a dy dx on the end. It's not as bad once you get the hang of it. Okay? So we have y squared plus 2xy dy dx. Okay? Alright, now, let's take a whole function. We've been working with just expressions, but let's take a whole equation here and look at our process that we want to do, okay? So the first thing, if I want to find dy dx for this relation, the first thing that we're going to do is we are going to take the derivative on both sides, okay? So I'm going to take the derivative with respect to x. I'm going to take the derivative of this with respect to x. Okay? Now what's the derivative of negative 4? 0. Okay? Now, I've got to take the derivative of each of these parts. Okay?
The problem is they're not all at x though, so some of them are y's.
Yeah, that's right. So, now this last term here is the easy one. The derivative of that's just,
2x.
yeah, minus 2x. Okay? That's just minus 2x. These ones here, though, I need to take the derivative with respect to y. So what would I have for y cubed? 3y squared. The derivative of y squared is 2y. The derivative of a minus 5y is a negative 5. But all three of those have times dy dx, times dy dx, times dy dx, because of the chain rule. Okay? So you differentiate both sides with respect to x. Anytime you're differentiating something that's not an x, you just tack this on. Okay? That's just the easy way to understand it there. Okay? Now, here's where you got to do a little bit of algebra, because we're told to find dy dx. We haven't found what dy dx equals yet. Anyone see how we could get there?
You can factor out the dy dx from the first three terms.
Okay, so let's take this term over to the other side. I'm going to take anything that does not have a dy dx and put it on one side. And I'm going to take everything that does have a dy dx, i.e. these three terms, and I'm going to leave it on this side. Now if this side had some dy dx's, I'd bring them over here. Okay? So basically get everything that has a dy dx on one side, everything that doesn't have a dy dx, get it on the other side.
Oh, and then eventually are you going to move dy dx to the other side where there's the 2x?
Well, we're going to leave it over here. We're going to take everything else over there. So I'm gonna factor out a dy dx, and left over in the parentheses, I've got a 3y squared plus 2y minus 5.
That's very sneaky.
And now, dy dx, I can divide both sides of the equation by this set of parentheses. So I've got dy dx equals 2x over 3y squared plus 2y minus 5. And that is the derivative of y with respect to x. And yes, it has x's and y's in it, but that's okay. Because if we want to find the derivative at a point on this graph, we'll just plug in the x coordinate and the y coordinate. And that'll give us the rate of change. Okay? Here's the basic strategy for doing all of these, okay? Differentiate both sides with respect to x. Collect all the terms that have a dy dx on one side and all the other terms to the other side of the equation. Then you can factor out the dy dx and then divide in order to solve for dy dx. Okay? Let's try a couple other examples. Okay? Here's one with parametric equations. Okay? Now, we can find the derivative with respect to t. Okay? Or notice here, if I want to find the derivative with respect to x, I want to find the derivative of y with respect to x. Let me see here.
You can plug the y in from the times.
Okay, yeah, notice y equals t. So I could plug in a y on each of these. Now notice there's a plus or minus. Okay, now positive 1 and negative 1 are constants. So we can just take the derivative and then put a plus or minus. Okay, but notice here I'm going to do x equals plus or minus the square root of y cubed plus 2y squared minus 5y plus 4. Okay. And now if I want to find dy dx, okay, if I do that on the left side, if I take the derivative with respect to x,
You get 1.
I get 1. Over here, I'm going to get plus or minus. I've got to use the chain rule. So it's going to be 1/2 times y cubed plus 2y squared minus 5y plus 4 to the negative 1/2 power times the derivative of the inside. Okay? Here's our chain rule. So what is it?
3y squared plus 2y minus 5.
3y squared
Plus 2. Oh, dy dx.
dy dx
I don't even know why I just said that.
plus 4y dy dx
Oh,
minus 5 dy
This
dx.
is the reason that we're saying that because we're taking the derivative of y is not x's.
Yes, okay.
Okay.
Plus 0, alright? So the derivative of 4 is 0 there, okay? Yes.
How can we write it that well? It's not 2y squared, it's y squared. Like the second side.
Oh, wait, yeah, I copied that. I copied that wrong. Thank you. Oh. And now I can't get it to erase. Okay, so this should not be a 2, which means that's not a 2, which means this should only be a 2 instead of a 4. Thank you. Glad you caught that. Okay, so now, notice here, I can take the 1/2 over to the left side by multiplication. I can take that, that whole thing to the negative 1/2 over to the other side by multiplication. Alright, so I would have plus or minus 2 times y cubed plus y squared minus 5y plus 4 to the positive 1/2 equals 3y squared dy dx plus 2y dy dx minus 5 dy dx.
Why is it a positive 1/2?
Because I multiplied both sides by that to get it out of the denominator. This is multiplication, so since it's negative, it's in the denominator. So I multiplied both sides of the equation by that y cubed plus y squared minus 5y plus 4 to the 1/2.
To bring it to the numerator.
To bring it over the numerator on the other side. Okay, Chloe?
So for all of the problems, the only difference is that the y became x and the x became y.
Well, the y we plugged in for the t, and then as we take the derivative of a y cubed, you treat it just like you would the x at first, but then you have to multiply it by a dy dx.
Why?
The chain rule. Y is a function inside the function of something cubed. So the derivative of something cubed is 3 times the something squared, but then you have to multiply by the derivative of that.
So it's a chain rule inside the chain.
Yeah. Okay? So now, notice here, we have the common factor of dy dx on the right-hand side. Okay? So I can factor that out. Okay? This is a dy dx times 3y squared plus 2y minus 5. Okay, and then I divide both sides of my equation by that. So dy dx equals, put it up here, dy dx equals a plus or minus 2 times y cubed plus y squared minus 5y plus 4 to the 1/2 divided by this set of parentheses here. The 3y squared plus 2y minus 5. Okay? Alright, so we're going from here up to there. Okay? Now, there are different ways that we could have differentiated this one. We could have differentiated both of them with respect to t. Then we'd have a dx dt and a dy dt. And that would actually give us a horizontal rate of change and a vertical rate of change on these parametric equations. Both of those, though, would be explicitly defined functions there. Explicitly defined in terms of t. Okay? So, any questions on number 3? All right. One last one here real quick. we'll take a look at the derivative of y cubed plus y squared minus 5y minus x squared equals -4. I differentiate both sides with respect to x. So again, let's run through this. What's the derivative of -4? 0. What's the derivative of y cubed?
3y squared dy dx.
Good. The derivative of y squared? 2y dy dx. Guys over there, are you with us? Okay? I just don't hear anything. Not saying you're not, but alright, so minus 5y is a minus 5 dy dx. And how about the minus x squared? Minus 2x. Do we need a dy dx there? No, because we're taking the derivative of an x. Okay? So good. So now we take the 2x to the other side. And all that's left over here are these three terms. And all three of them have a dy dx. So we can factor that out. And what's left is a 3y squared plus 2y minus 5. Whoops, and that's actually step 2. I got carried away a little bit. Okay, so there's our step 2. Collect all the terms with a dy dx on the left and all the other terms to the right. And then we factored. I got really carried away, sorry. So then dy dx is that 2x over the 3y squared plus 2y minus 5. Okay? Now notice here, guys, we're not necessarily dealing with a function. In fact, this one is not a function. That's what this graph looks like. It's kind of cool looking, huh? Your TI calculators can only actually do functions. So it can't graph this for you. Desmos could. Alright? But you'll notice here, if I wanted a point on the graph and to find the slope of it, at that point, I'd have to plug in both the x coordinate and the y coordinate. So at 2, 0, it would be 4 over -5. -4/5. Okay? I'd have to plug in the 1 for x and the -3 for y to get a 1/8 is the slope there. Okay? So that's all the differences there. Okay? Alrighty guys, we'll do more of this tomorrow. We'll see ya.